We have here a triple integral, and this is a triple integral that lends itself very well to cylindrical coordinates. It's the triple integral of the square root of x squared plus y squared. That already is a hint that we should be thinking cylindrical coordinates, because the square root of x squared plus y squared is just r. So the integrand is going to simplify if we're able to use cylindrical coordinates. And then the geometry of the integral is that we're integrating within a cylinder. X squared plus y squared equals 1 is the cylinder that's pictured here. So that's cylindrical, and that's another indicator that we might want to be using cylindrical coordinates. We're cutting this off at z equals 4, so you can think of the top here as z equals 4. And then, so we want this portion of the cylinder below that. And above this, and this is a paraboloid, z equals 1 minus x squared minus y squared, is a downward facing bowl or paraboloid. So the bottom of this cylinder is kind of cut out by this downward facing bowl. And that's, not a perfect representation of it, but we get the idea. We're looking for everything above that bowl and below the plane z equals 4. So in cylindrical coordinates, right, we have square root of x squared plus y squared is just r. We have x squared plus y squared equals 1. The surface, or defining our solid anyway, is r squared equals 1, right? So that's r equals 1 for that portion. We have z equals 4 in cylindrical coordinates is still just z equals 4. Remember, the cylindrical coordinates don't care about z. They only are caring about x and y, and they're turning x and y into polar coordinates, basically. And then we have the paraboloid, 1 minus x squared minus y squared. That's 1 minus r squared for the bottom of this solid. With all of that, right, with this work on kind of describing this region and this solid, we can set up the integral. In z, we have z below going from 1 minus r squared, right? It's going from this paraboloid, 1 minus r squared, up to z equals 4, this plane at the top that's cutting off the cylinder. So z goes from 1 minus r squared up to 4. The thing we're integrating is r. Since we're going in cylindrical coordinates, we have an extra r. We have dz, dr, d theta. For r, right, if we're looking down now on the xy plane, looking down on this thing from the xy plane, it just looks like a circle in the xy plane with radius 1. So r goes from 0 to 1, and theta goes all the way around, 0 to 2 pi. So that is our integral that we can do. We can do the first of these. We don't need to go all the way here, since this is not a terribly tricky integral to do, but we have r squared. We integrate r squared and get, this is r squared, but it's with respect to z. So we integrate that, and we have r squared z from z equals 1 minus r squared up to z equals 4. And then we have the dr d theta. So that will look like an integral from theta equals 0 to 2 pi, r equals 0 to 1. When we plug in these values, we have 4r squared minus r squared times 1 minus r squared dr d theta. We'll leave it there. I think that we can handle the r integral here is just the power rule, and the theta integral is just constants. Nothing really doing with the theta integral. But that is the hard part of this problem, and that is an example of why cylindrical coordinates can be useful in triple integrals. If there's anything cylindrical in nature with the solid, or any kind of x squared plus y squared type stuff in the integrand itself, then we might want to think about cylindrical coordinates, and we can get some of the savings that we saw here. This one would be pretty hard to set up as an x and y integral. If we did it, then we would eventually be switching to polar coordinates to make it worthwhile anyway, which is, in a sense, equivalent to doing it in cylindrical coordinates.